Good day, grade 12s. Today we are going to talk about chemical equilibrium. Our focus will be on the graph. So remember, we have factors that do affect equilibrium. Those factors has to do with concentration or the amount or number of moles. It also has to do with pressure and volume. And lastly, it also has to do with temperature. So this time around, our focus will be on the amount or the concentrations. So now, I want you to check this illustration out. I draw a seesaw here. So let's just assume that we have a seesaw like this one here. And now we have two persons. Can you see we have two babies on the left hand side playing on top of the seesaw, and we have one individual on the right here. So now I want you to assume that whatever that is on the right, it has to do with the product that is on the right. Can you see in this reaction on the right we have AB, and then I want you to assume that whatever that is on the left, which is the reactant obviously, it has to do with A and B separately like this. So the seesaw is balanced. In other words, the equation is balanced like this. But I want to ask you something to say. Now, what do you think will happen to this seesaw if now we decided to add more of A on this system? In other words, just assume that this little baby A here, let's just assume that we give him or her a heavy object, just like a stone or any object that is heavy. What will happen to this seesaw? Obviously, it will tilt. It will never remain like that. And when it tilts, even this ball here will be disturbed. It will roll, right? So I want you to pause the video and try to do it and try to figure out what will happen when this baby A or it's now or a heavy object is now been given to him or her. So will the system tilt like number 1 here, or will it tilt like number 2? And then what will happen now? How are we going to apply Le Chatelier's principle to predict what will happen, to predict which reaction is going to be favored, reverse or forward? Then what happened to the product in terms of increment and decrement? What happened to the reactant, and so on and so forth? So now, if we were to add more of A, it simply means that the system is going to be heavy this side on the left hand side than this side. And when the system become heavy this side, the system is going to be disturbed and it tilt like number 2 here. When it tilts like number 2, even the ball will be close to this girl here like that. And that's what we call disturbance equilibrium. Now, when we have a situation of that nature, we apply Le Chatelier's principle to come and do what? To come and solve the problem that we created. So how will Le Chatelier's come and react to this situation of this nature? Le Chatelier's will come and return the ball. Remember, the ball was in the middle, right? So, and now it's now close to this girl. In other words, Le Chatelier's will come and be applicable in this manner, that the ball should be shifted to the right. When we shift the ball to the right, we are favoring forward reaction. In other words, adding more of A will result in favoring the forward reaction. And when we favor the forward reaction, whatever that is on the product must increase. Whatever that is on the reactant side must decrease. If you are not familiar well with what I'm talking about, please kindly check my previous video. You will find more detail on what I am talking about. So now, this simply means that adding more of A, we are going to be favoring forward reaction, because when you add more of this A here, the system will tilt like number 2 here. And then when it tilts like number 2, it is because it will be heavier on the reactant side than on the product side. As a result, it will go down like this, like this system that is indicated on number 2. So now, I want to graphically illustrate what I've just said now. I want, let me draw my y-axis, my x-axis, and indicate that on the y-axis, let's assume we have the amount, or let's say the concentration. Then on the x-axis, let's say we have time. Let's say time in seconds. And then let's draw now the graphs. So normally we know that when we started with the reaction, the product is 0. So this means our product graph will emerge or start from this corner here, because that's where we have 0. The product one will start on top like that until it reaches equilibrium. Now we can say A has reached equilibrium, especially here. Now let's go for B. B, now it has reaches equilibrium like that. Let's go to the product now. The product can't start from the top here, because when we start now, we don't have the product, so it will start exactly here at the corner, because when we started the reaction, the product was 0. Now we can say the system is at equilibrium, right? Now, when we said the system is at equilibrium, obviously we are simply saying the rate of forward reaction is equals to the rate of the reverse reaction. But now we want to disturb this equilibrium and find out graphically how will it look like. So let's say, let's find out what happened if we add more of A. So I want you to remember what we just talked about as far as this seesaw is concerned, to say, if this first personnel represent A, the second one represent B, the third one, which is represent AB. Now, if we add more of A, the seesaw will experience some heaviness here on the reactant. As such, it will tilt like number 2. When it tilts like number 2, this ball that is in the middle will be closer to this girl here. And we will have to call Le Chatelier's principle to come, or apply Le Chatelier's principle to come and rectify the disturbance that we did. Le Chateliers will come and do what? And they roll the ball back where it was, meaning that we will shift the ball to the right. Shifting the ball to the right, it simply means that we are favoring forward reaction, because we are going to the right. If we are shifting the ball to the left, it simply means that we are going to say we are favoring the reverse reaction. And in this case, if the ball is like here, the system is disturbed, the ball is closer to this girl, we can't push the ball to the left and reverse again, because it will be like we are contributing towards the problem instead of solving the problem. So now, let's graphically represent what I've just said. Where is A? If you check the color coding, A is this one. So if we said we add more A, it simply means that when we go up, we add. If we go down, we subtract. Now the question says, what happened when we add? Meaning that this is just like a Cartesian plane. You know, in a Cartesian plane, when we go from here to 0 going to the right, we are adding 1, 2, 3, 4, 5, 6, and so on and so forth. And then from here to 0 going on top or going up, we are adding. But from 0 going down, we subtract. Even going to the left, we subtract. So this simply means that here for A, since they said we add, we are disturbing the equilibrium by adding more of A, we must just draw it like this. Then it goes up like this. If it says we subtract A, or when some of the A has been removed, then the graph was not going to go up like that, or the disturbance was not going to go up like that. It was going that it will have gone down like that. However, in this case, since we are adding, we just disturbed by writing the vertical line going up like that. However, now what will be the consequences of doing that? We apply Le Chatelier's principle. What did Le Chatelier's principle, or how will Le Chatelier's principle going to be applicable? We know that when we add A here, the system will shift like number 2, right? Then we invite the ball will be closer to the girl. We invite what? Le Chatelier's principle to come and shift the ball to the right. Right? When we shift the ball to the right, we favor the forward direction. And when we favor the forward direction, what happened now to whatever that is on the right? Remember, we shift from left to right. Whatever that is on the right, if we are shifting to the right, whatever that is on the right must increase, whereas whatever that is on the left must decrease. So in this case, it simply means that whatever that is on the right, what is it that is on the right? It's AB. It simply means that AB must increase, whereas A decrease and B decreases. So how do we tell whether it's increase or decrease graphically? This A that goes up, if we're saying at the end of the day it will decrease until a new equilibrium is established, it simply means that you must now see a curve that is going down. In other words, when we curve down, it's decrement. When we curve up, it's increment, meaning that A must curve down like that, because we said it will decrease at the end of the day. What about B? Even B, we said it must curve down, so it must curve down like that, because that's what we found out as far as Le Chatelier's principle is concerned. But what will happen to AB? We said AB must increase, and I mentioned to say increasing simply means that it must curve up like that. So that's the graphically representation of what happened when we add more of AB using the seesaw. Now I want to repeat this example, but this time around I won't use this seesaw rule. I want you to copy this seesaw down and apply it to the next example that I'm about to give now. I decided to omit now the seesaw to find out if you understand what we did here. So let's now uh, do it in this way again this time around. Let's now say what happened if we add more of AB. So we are still going to use the seesaw rule. However, I don't want to write it here to find out if you did understand what I talk about on the previous slide. If you forgot, kindly go back and listen to the previous slide or to what I said in the previous slide. So if we add more of AB, look at it. AB is on the product. It simply means that it will be more heavier on the product. Then as a result, it will tilt down like this. Even the ball will be on the product side, close to the product side. From there, we will have to apply Le Chatelier's principle. Le Chatelier's principle, when it comes, or when we apply Le Chatelier's principle, we will shift the ball to the left. And shifting the ball to the left simply means that whatever that is on the left must increase, meaning that A must increase, B must increase, AB must go down this time around. From there, how do we graphically represent what I have just said now? We represent it in this manner. If we said we add more of AB, where is AB on the graph? AB is the product. It must start here at 0, AB, meaning that we are just going to add a straight vertical line going up from what? From AB, like that. So there is it. From there, we mentioned to say at the end of the day, it must go down. Why must it go down? Because adding more of A, it simply means that it will be heavier. If you think about our seesaw, it will be heavier on the product. As a result, it will tilt like this. From there, now we can say the system has been disturbed, and we have to call out Le Chatelier's principle to come and rectify the disturbance. When Le Chatelier's come, he will shift the ball back to the left hand side, and in doing so, we are favoring the reverse reaction. Favoring the reverse reaction, whatever that is on the reactant must increase, but the product must decrease. That's why the product curve down like that. So what will happen to B and A must curve up to indicate that there was indeed an increment, curve up and curve up like that. So that's the graphically representation as far as the amount of concentration of the reactant and product is concerned, graphically under the chemical equilibrium chapter or topic. Thank you so much for watching this video. If you find this video useful, kindly hit the thumb up.